Yeah, you have to always get an angle and looking like in the distance like the mission frame of mission. Wasn't that impressive? Firstly, so I could sort of like
once you change, once you do anything, then you have to wait.
Yeah, I somebody.
You have that chapter.
Probably still.
But very few.
I had a lecture So when you start doing it, just come up. So you have to make sure it's really so it's not going when you put out dim the lights. But I'm not going to do it now. Yeah,
That's where I worked on the girls today. They could
yeah, the problem is I think yours is mine's the newer one. I guess they're holding out, right? They're waiting to see. When did you decide?
What did it have to go?
That's probably more.
Yeah, that's the hard thing to do. So you actually get one. I'll start. Did you get the mic? Alex? No, it's actually most of the time they have it. They have
Hello, does it work? Yeah. Okay. So, hi everyone. Today, welcome back to the third session of deep learning. The topic of today's lecture is the following. First, I'm going to talk about convolutional neural networks. Then I will talk about recurrent neural networks. These are some of the very popular types of neural networks for particular applications. Then we'll talk about word vectors or word mechanics. And then in the second part of the lecture, we'll talk about ongoing work at the Google Brain project. So before I begin, I want to revisit some of the topics that we discussed yesterday. The first topic was some practical advice of how to train neural networks. And then I discussed the usefulness of having neural networks. Namely, you can classify nonlinear data. And then I talked about deep learning, the definition of deep learning. Why is it related to neural networks? Then towards the end, I talked about the idea of autoencoder and unsupervised learning algorithms. And then I talked about the idea of pre-training. So maybe there was a bit of confusion towards the end about autoencoder, pre-training, and so on. So maybe I talk about that and then start today's lecture. So yesterday I was talking about the idea of autoencoder. And maybe a vector of 3 or 4 dimensions is, and then a neural network. So you have to learn the matrix W, W1, W1, maybe another W. Let's call it the matrix W and V. We want to learn W and V in such a way that X prime is very close to X. So you minimize during training, the goal is to minimize the distance between X and X prime. Right? And X prime is a function of X and W and V. Right? Autoencoder. So this is a shallow autoencoder with one hidden layer, trying to learn the encoding that can reconstruct the image. Now, in around 2006, people use it for something called pre-training. So the idea of pre-training is as follows. So let's suppose you have a deep network. Let's suppose that you have a deep network like that, right? And you have W1, W2, W3, you would like to train, right? Maybe at the end you want to predict some label. Okay. It turns out with a deep network like that, if you have random initialization, it might take a long time to train, or maybe it will converge to batch rapidly. Okay. So people say, well, an idea to use unlabeled data to come up with better initialization for W1, W2, W3 is as follows. So first, you check this pattern out, and then you train the autoencoder. Okay. So W1 prime is an automatic. Right? You learn, but then after you're done training, you from training. After you're done training, you end up having W1. Then you multiply with your data, right? And then you feed forward, and you end up with H1 of X. Okay? And then you use H1 of X you check this matrix out, and then you learn this is one. This is another orthogonal color. Okay. And then you learn W2. So after having W2 and then W1, then you do a feed forward one more step to have this layer, and then you keep going. This is unclear. Yeah.
This is probably a bit of a silly question, but if you found a good, for example, in your diagram here, a good three-dimensional representation of four-dimensional inputs, why go back to a four-dimensional space? Why not just work in a lower-dimensional space from that point onward?
Oh, so you're saying why don't you?
So once you've learned that representation, you already have a good three-dimensional representation of your four-dimensional input space.
Yeah.
So why not just work with that in your supervised algorithm instead of?
Oh, I see. So why don't you start on the label just right here, right?
Sure.
Is that one label? Well, so the idea of having a deep network versus a shallow network is that what I told you yesterday. If you want to have a good shallow network, right, you need a lot of neurons in one layer to model that. Whereas if you have a deep network, you might need less neurons per layer. So if you stop here and then try to learn why, maybe why is so nonlinear, but you need a lot of these neurons. Right? But if y is nonlinear, there's another way to do it is to have a deep network. And you could learn end to end, but it's too difficult. So you have to make it layer-wise retraining to approximate. So first, to try to reconstruct X, and then after that, try to actually. This happens here.
In the second autoencoder, won't you just learn the identity function?
Here?
Yeah, because you have three neurons in the middle there.
That's a very good question. So the first answer is because it's nonlinear right here, it might not be exactly identity. But I have another answer. So turns out so far, what I've just told you is, input, and then maybe in the next layer, the number of neurons can be smaller than the previous layer. It's gonna be small, right? But sometimes you don't have. Sometimes you want something like this. Is the input, right? And then sometimes you want something, right? Or maybe more. An autoencoder with a hidden representation larger than the input is very redundant. So it's very redundant. What we learn is basically trying to, make W1 an identity function and the rest means zeros or something like that. So it's not useful to actually learn W1 when this is very redundant like that. So a way to avoid that is using something called star autoencoder. The idea is so there's many variations of sparse autoencoder. One is basically just say, in addition to the reconstruction objective, in addition to the reconstruction objective where you have X, and then W1, you really want the hidden let's denote this H of X. You want H of X to be sparse. L1 penalty on your dataset. It's like penalizing the absolute value of data. Okay? And then what you end up is a redundant representation maybe, but very fast. And for a given input, maybe a few of the pixels, a few of the neuron would be non-zero, for the rest would be zero. So L1 is one kind of penalty on the hidden representation, but many people use other kind of penalty, for example, L0, or maybe the KL convergence between H1, and some target distribution. So if you Google for sparse or autoencoder, you might end up with all the variations, but maybe I just want to talk about one variation in this section. Is that okay? Okay. Any other questions?
You say that the hidden layer is redundant. Do you mean that it forms in over complete space?
Can you ask the question again? I didn't hear it very well.
So when you say that the next hidden layer will add more nodes to it, and then it becomes redundant, but do you mean that it forms in over complete space?
Yes, it's overcomplete. So this is overcomplete, right? So the number of output is much larger than the number of input. So it's totally redundant. If you don't enforce, then it's possible.
I mean, that wouldn't be the case if you had multiple hidden layers, and you had.
Pardon?
That wouldn't be the case if you had multiple hidden layers, and one of the hidden layers just happened to have more.
Yes. You only do this if you have one of the layer being overcomplete.
Yeah.
Okay. Any other questions? So let's talk about convolutional neural networks. Some people also use it in comments. So if you Google literature, sometimes you see the word complex somewhere. So before around 2011, in computer vision, a lot of people use something called handcrafted features. So handcrafted features are something like switch on off, etc. And they work really well for small dataset. But it turns out that around 2011, after we used convolutional network and using with GPUs, the results of CONNET are usually better than handcrafted features. And that gives like dramatic change in the field of computer vision. And I think and it is a very important concept to learn. So let's go back to our original idea of neural net, right? So let's suppose this is the input, right? This is input. This is could be an image, right? Maybe a 1D image for now. Okay? And then we want to learn some representation, and then try to predict the label. Okay. Representation. So and then every neuron will be connected to the input image. Okay. A problem with this representation of this setup is that let's suppose that your input image is really big. Let's suppose that your input image is 100 by 100 pixels. Then this image is a 10,000 dimensional vector. And then every neuron in here will get 10,000 connections. So let's suppose that you have like 1,000 neurons, 1,000 features, very small, right? then you end up with 1,000 times 10,000, which is a lot of connections, right? Okay, and medium. Right? So that is a very expensive representation. So people have thought about how to avoid that problem. And then they look at images and then realize that pixels in a local region of an image are correlated with each other. But pixels are very far away and are not correlated with each other. So let's give an example. Let's say I take a picture right here. Then the information around here will be very correlated. But the pixel here and the pixel over there are unlikely to be correlated. So they propose, the first idea that they propose is the idea of local receptor field. So again, let's suppose for now we have a 1D image, right? Then we have a neuron. Instead of connecting to everything in the image, just only connect to only the few pixels. Right? This is the top left corner of the image. This is the next area. And then, with that idea, you end up with a representation that you found that has less parameters compared to the original fully connected information. So how do you do backdrop with this? Right? Assuming that having local connection. So one way to do this, a very naive and simple implementation, is to suppose that all the connections are there, right? With the idea of it. And then you magic spectrum multiplication using the fast magic spectrum multiplication, and then doing feed forward like normal. Okay. And then when you do backdrop, you will compute the gradient for all the parameters. But for the ones that are not connected, you don't update the parameters. Okay. So is it excuse me? Is it still seeable or is it too far away?
It's still okay. It's still good.
Up to right here?
Keep on going.
Yeah.
Stop.
Okay, yeah. So here I say assume that the network is just fully connected, but with 0, 1 for the empty connection, and then do overflow. As usual. You do forward right normal, and then backdrop as usual. Okay. And then backdrop as usual, but only update the parameters that are not here. Right? Is that clear? Okay. So local receptive field network reduce the number of parameters significantly, but that's not too much. Now we can do even better. So what we can do, let's suppose this is a network. This is basically local. This is local network. Okay. Another idea is to say that all these copies are the same. What I'm saying is that let's say this is W1, W2, W3, W4, W5, W6, W7, W8, W9. We'll impose the constraint say W1 equal to W4, W2 equal to W5, and W6, 3 equal to W6. So strictly speaking, these whites are the exact copy of these whites, and these whites are copy. And because this looks pretty much like a convolutional operation, right? You take this and then you replicate it in many space in the image. Right? Suppose that you have an image like that, then you have a way that keep copying in all the position of the image, and that action is called convolution, and that's really enhance the name convolution. Now, how do you do backpropagation with convolution? Right, so I will tell you a naive implementation, but a faster implementation you can think about later. Right. So assume a local receptive field network. Right? So a front net is basically a local receptive field network that I showed you over there. Okay? And then what you do is you do forward prop. As usual. You do forward prop as usual. And then do back prop also as usual. Then after you're done, you have the gradient of all these parameters. Okay? Then first you sum up the gradient. So you say dj over d. You do this action. You do dj over d1 plus dj over d4 dj over d7. These are the ways that I share with each other. You sum it up, right? And that's the update of W1. Okay. And then you set W2, set W4, W1, and then you set W7, W5. Right? And then you do the same for all. Question?
Wouldn't it make more sense to average the gradient out
It turns out that the sum is an alpha. The sum is the correct ratio, which you put average to. That's basically changing the learning rate. Yes. Question?
Yes, so I'm trying to understand intuitively, you said that it's equal to 0, but you are actually considering them to be different, and that's why you are calculating the differentials against each. All of them.
Yeah. When you do backprop, right, you get a grade for this one,
Right.
you get a grade for that one,
Right.
you get a grade for that one, right? Because of backprop,
Right.
right? But because they are shared.
Okay.
They are shared by this constraint, right? This is what I said. Should be, right? And then you do something like that. Now, that's a naive implementation, right? Because I try to be really redundant. I say, I have an explicit representation for if you want, explicit representation, right? Which could be clever in your code, not to have that. Okay? But this is, mathematics is what it should look like.
And the second question I had is, intuitively, why does this work? Why does representing just W1 instead of all those three, why does that work? I'm trying to understand that, there we assume the weights were 0.
Yeah.
And now here we are assuming,
There's a couple of steps here. Number one is this connection is 0.
Yeah.
Right?
Yeah, so that is the same as that one.
Right. So that's locality. Okay. So this is locality.
Yeah, that makes sense.
Everything. Okay, that's cool.
That makes sense.
Okay. So the second question is why copy in is a good idea? Okay. So that's a great question. So let's think about it. So far I just told you how to do math, right? So let's think about why is it. Why is that a smart idea? So it turns out that in
What does that stand for?
SEL local research. Yeah, sorry. So first, we wanna let's move one more step and say what do we do if the input is two-dimensional? Okay, so far this is a 1D, but I want to do it for 2D. So for 2D, what you see is something like this. So let's say you have an image. And again, the input is about a pixel, and the pixel has some value. Right? It's a 2D input. Right? So a count net on image is basically the same. So you have a neuron that 6 pixels here, and then you copy it over to the next position where so this neuron, the weight for it, will be copied to the next position. Maybe that's clear. So maybe let's keep with 1D first, and then we could think about it. Okay. So it's hard to actually understand it in 1D, but I will try. Okay. So let's suppose that in 1D, if you have some pixel, if you have some object, but it moves. If it moves, so let's say you have an object right here, and the concept. This is the same object, but it moves downward for a couple of pixels. And you want your reference network to say, it doesn't matter where the object is in the image, but as long as it is in the image, just say 1. Right? Then concept is a good idea because this filter of that object is being copied over in different positions. Right? But we need one more step. So that is just a convolution step. One thing that we could do is called max pooling. I need so the concept as I showed earlier, we have something like that. another action for max pooling, which is you take the max. You take the max of the activation of these two pixels, then you also take the max operation. And that means as long as the object is in these 3 pixels, then the value of this pixel doesn't change. And as long as the object is in the 6 pixels here, then the value of the pixel doesn't change. Does it make sense, or that's okay? So let's suppose that the value. So right now, let's say my input is 0, 1, 0, 0, 0, 0, 0. Okay. I have some weights here, 31, 52, 53. Then after my multiplication and then taking the max, I end up with 52. Okay. So let's say that this pixel gets shifted so that I end up with the input that looks like this. Yeah. Then after I multiply, this is 4, this is 5, this is 6. After I multiply, I ended up with value of 55. And my constraint over there is W2 is equal to W5. So that means the output of the network for these 2 images right here are the same, which is a desired property if you want to do object recognition when the object moves around in the image. You have a question?
So, in computer vision, when we apply a convolution filter, then we move the kernel to the next block. We move by 1 pixel. Okay. But here we are moving by 1 complete block.
I draw this picture. This picture I like this because it's clear to see. But you could imagine you move complete just one pixel away. That's fine. Okay. For visualization, I say the step is basically equal to the size of the filter. But you could say that the step would be just 1 pixel away, and that is all. Right? All the mathematics that I wrote to you here still apply. Yes.
Does this give you a way of handling multi inputs of variable sizes?
We don't have that yet. So if you have an image of variable size, you have to crop the middle part of the image and use it as the input here.
But if you use convolution network, it will have a larger depth, and you will end up with the same size of that.
You can do it. You can do it. I'm saying in theory you can, but it's not it's not very common in field. You could actually think about it that way. The problem is that if you have different size images, then the output image, right? Think about this one is the output image right here. Could have also different size. And then if you move forward several layers, you want to do classification. And then the classification we're going to have variable size parameters, right? If you think about, you want to connect this to do classification. Right now you have 3 weights. But if it's variable size, you want to end up with 4 weights too. And that's the one you can't do in machine learning.
So what you're saying means that in every layer the weights are different. They're not shared across the.
No, they're not shared. Okay. Okay. I have questions coming from you too. So yeah.
So if we do forward prop as usual and back prop as usual, are we really saving any computation power?
Oh, I see. That's a good point. Turns out that combat is usually faster than dense network. So far here I'm just talking about how to do mathematics, right? How to do it in an easier way to understand. But obviously, this operation right here can be called by some standard library called, in MATLAB you compute control cost. right? And that's faster than doing explicit multiplication. That's the first thing. Maybe in comp, you could do G transform or something like that. But it's also faster, right? Also thing that you could do to make it faster. But you should implement this thing first, and then you look deeply inside the code where you can optimize, right? And then start optimizing, right? Because I want to present the easier way to discuss. Any other questions? Thank you. Lean forward.
I think we look both of them. Yeah, if you look that one. Yeah. On your right.
Okay, so a normal concept would be multiple layers, so it's not just that. Usually people construct a concept like this. Right? Do convolution. Convolution, and then max. And this can be considered as another coupled image, and then you can replicate this structure forward. Okay. What people also typically do is the idea of local contrast normalization. So what they do is that in addition to this layer, you take the pixels here in a small area of the image, and then you compute the mean, and then you take the value and then subtract the mean. So basically, this value replicated here but subtract the mean. This value replicated here but subtract the mean too. And then divided by the variance. Or standard deviation. So this idea here, subtracting the mean and divide by the standard deviation is called local contrast normalization. So it actually mimics one of the very interesting properties in the brain. Only that if you take an image right here, right, and then you also turn off the light, then that's it. Almost without recognition for that image is almost the same. So the light representing the mean of the image. Right? And you could apply backpropagation using through the local contrast normalization, through the maps, and so on as normal. But a deep convolution will usually replicate this into many stages.
Some people implement contrast normalization across filters, across layers of filters, and some people, so that would be, say, Alex Krzyzewski, and then Jan array and so on in the web, but they implemented doing context normalization over the image patch.
I think Jan Legrand, the guy who proposed the idea of neural network and convolutional neural network, normally does this. So this is more standard. Doing mean subtraction and divided by standard deviation over locality is more neutral. But it was Alex Krzyzewski, which is a guy who would apply this principle across filters. But I haven't talked about across filters yet, so I will visit that idea. Is this idea clear? I want to make sure that you can at least do a forward prop, and once you can do a forward prop, you can work it out how to do a back prop.
Is the reason doing this subtraction and division by the standard deviation to work with smaller numbers? What so that we reduce everything to a grayscale, so it's easy for us to compute. Why do we do that? Why are we trying to? Why did we do the local contrast normalization? What did it give us?
Oh, so sometimes you take a picture of a car when the light is on, and you take another picture of the same car when the light is off, a little bit darker, right? For you, that's the same car. For computers, that's a different car, because that's such a non-linear transform. Right? Local contrast normalization will get rid of that. Okay. I hope that makes sense. I think you take a picture and then you take another picture with that, and then you load it in MATLAB, subtract them, then you will see what I'm talking about. I have a question in the back. Sure.
Can you just say again, sorry, what's it the mean of that you're subtracting?
So the mean across the pixels, yeah.
So it's the two,
yeah, the mean of these two. So you take this value,
okay.
you sum it up, divided by 2, and then subtract that from this one. Subtract that from Is that clear? It's the mean in a local region of the image.
Okay.
Yeah. And the variance in the same local region.
So in practice, it's a lot more than 2, I guess, if you're meaning that you're.
Yeah, you could do it more than 2, right? You could do it 10 by 10. Everything so far is just an idea, right? The size of the filter, you could make it like 10 by 10, not just 3 pixels, right? Idea back.
All right, so we basically hard code lots of domain knowledge there. So this could not possibly, as it is, as you described it, is not possibly will work for outside of the image recognition domain, right? Because we encode independent structure there, and there's contrast minimization and stuff like that. So for some other domains, we will have to construct a network by hand. Is that it's not possible?
I think
to learn that, right?
Yeah. I think it's fair to say that a lot of these ideas in here are only applicable for maybe images, maybe videos, right? And maybe audio, right? Maybe some text, right? You could argue that it could be applicable to text too. But for general vectors, right? If this is just a random vector, then I would say that's not applicable.
I just wanted you to say that.
Yeah.
No, I disagree with that. Because the principles that we're looking at here, which are translation invariance, local transformation invariance, intensity invariance, we often have to do that for all data sets. You need to get invariances. I mean, that's the basis of machine learning.
But if you do max pooling, if you do local receptive field for just a general vector, I'm not sure if that's.
I think it's important to do it if you're doing language or if you're doing any data mining classification task.
Yeah, okay.
you always have to do.
Yeah, I am more reserved, so I say it's all, I think, I don't have experience applying this for all the domains, to be honest. My intuition is that it only works for, natural data like images, video, audio, and text. But Nando said that it might be applicable for other vectors too, and I think that might work. And I don't know, to be honest, because I haven't tried. I have limited experience applying this to general machine.
How do you choose the convolution period? Here you choose as 3, so what's the difference?
So again, anything to do with hyperparameters. One is that I did a PhD and then I know how to set hyperparameters for neural networks. Okay, so the better answer is that you should use what I said yesterday about grid search, random search, and even better, Bayesian optimization. That's the reason why. Nando's talk should be even more appreciated. It turns out that it's non-trivial, right? If this question comes up again and again and again, and especially in a plot net, you not only have a couple of hyperparameters, you have tons of them, right? So you need a smart way to pick hyperparameters. And I think the work being done at Nando's group and some other groups suggest that if you use Bayesian optimization, you can come up with an architecture that's even better than human classic network. How about that? And I think that seems to be very promising.
Does it depend on the image dimension or object size? The Bayesian optimization is very general, right? So you take an existing network, maybe someone constructed it, right? And then it would play around with it, try a bunch of hyperparameters, and then suggest what's the next thing you should try. But it's true that it's dependent on the data set.
That's okay. We call that contextual Bayesian optimization multi-task.
Yeah.
Can local contrast normalization be applied as a pre-processing step to the input?
Yes. People have done that.
Yeah, my question is, how do you apply the back propagation on the max pooling layer? So how do you get the derivative of the max function?
Yeah, one naive implementation is you keep the index of the max using forward prop. Right? So which of the two would be the max? And then when you do back prop, you only change this parameter. Any other questions? More questions?
But to make sure, so if the object is rotated, that's totally a different object.
Right. So again, this is limited invariance knowledge that you could actually incorporate in the network. Things like rotation, right, scale invariance are not incorporated, right? Because it's not the user, I guess. But you could come up with other type of networks. Any other questions? Yes?
Why choose the maximum in the second?
Max? How do I choose max?
Why choose max?
Oh, because of this idea right here. Right? The max means, so after you multiply, you end up with a lot of values. The max only saying what is the most prominent phenomenon in the image that you see. Right? You can work it out. So let's say you take 0, 1, 0, 0, 0 and multiply on this. Right? Then you get some values, right? And then you get
what if it's one decimal and it has a very strong negative network?
I see. Then the W2 who learned that W2 has to be also a negative number.
we can take this offline. But okay, if you're not happy with the max, people also try to look at the mean, right? Look at the average between these two pixels. That's one thing. People try a lot of other ideas too. I think the most prominent, the most successful is the max.
So are you grayscaling the image before doing this, or can you just correctly
So far I haven't talked about images yet, but we could, it's hard to draw it in a 2D image really, but let's try. Let's try. Okay, so how to apply concept to 2D data? So let's suppose you have an image. This is a grayscale image for now. Right? So you could have a filter and look at this part of the image. This part of the image. And then you have also a filter and look at that part of the image. The complex and all the whites here are the same with all the whites here. So you can copy and position and then replicate it. Right? And after you do that, you end up with an image. Maybe, okay. After you do convolution, you end up with an image. Is that okay? And then you do max pooling, and then you end up with another image. So the question is, this is a grayscale image. What do you do if it's a 3-channel image, right? That is the question. Turns out you can stack 3 images next to each other. R, G, and B, right? And 3 images. And this pixel, this neuron, instead of looking at one image, it will look through 3 images. Okay? So it will, when it applies at a position, it will see the red picture, green picture, and the blue picture. Okay? Is that clear, or is there a question? So, but it ended up with one image only. Now, so one image is actually very limited. Can we do more than one image, right? The answer is yes. So it turns out yes, you can do that. You could apply the same principle, but replicate it into many maps. Okay? So you have another filter and look at this position, and then it will generate you another image. Okay? It's exactly the same idea, but it's a different filter. Okay? So you could draw this picture outward like this, right? So you have a stack of image and input. And then you have a stack of image in the output. And let's suppose that you have 3 filters per position, then you end up with 3 images. So the word filter to mean the weights are associated with this neuron here. So here I end up with having 3
convolutional kernels or free filters, and I ended up with three. Right? And then you can do mask pooling per image. So I end up with three other images. Right? This is mask pooling. And then you do local contrast normalization. Local contrast normalization. Now you have a choice. You could do local contrast normalization per image, or you could do local contrast normalization across images. Okay, and then you take that and then replicate it many times. So that's basically a concept, right? I hope that you don't find that too complicated. Questions? No question. Too easy or too hard? Too easy? Good. Alright. You have a question?
I do. This is more to do with how you code this. So Smart Interpret and Liam have recommended this modular architecture where you have objects layers, and each layer has a format, has a backward message and a derivative. So those are your methods. And that seems to make sense. One thing that they don't often talk about is how to schedule visiting layers and so on for different optimization algorithms. And also, do you store the weights in the layer, or do you store the weights separately? What would you advise people to do when designing an architecture?
Okay, so first for CompNet, I implemented many versions, but I think your way of implementing, I think it's more modular and probably easier if you try different kind of architecture. But for speech, I usually implement this step. I usually call comp2, where comp2 is something like in OpenCV you have comp2, convolutional in 2 dimensions, so I call comp2. In MATLAB, there's a function also called comp2, and then you call it, and then you end up with this, and then you do mask pooling and so on. It turns out the backprop is also a comp2 as well. The backprop is also a comp2, so the backprop in the backprop I also call comp2 again. So the entire thing in here is done using comp2. If I code a convolutional network. Now for a general neural network, I think your way of doing it will be more modular. But this is probably one of the fastest way. Now we have comp2. What happens is that the library will check, how many images there are, what is the size of the filter, what's the size of the image. If the size of the filter is small enough and the image is large enough, what they do is they convert everything into FFT and then do it in an FFT. But if the filter is large enough, they will do it explicitly. So they take the filter and then do a for loop to multiply every position in the image. So that's how I would implement it when I do a concept. But a general implementation, then you might. I want to continue the concept for a little bit. So it turns out that in a standard concept will have many layers. So people usually do something like this, right? You take an image, and then they do this a convolution. So
or something like that, and then you add up the output, and then you do max. You have max pooling, and then you do FCN. You have something like that, and then many layers. You end up with maybe the output of the last LCN. And then plug it into a classifier. So it turns out that a better classifier is like a two-layer neural network. So this is densely connected using specified linear unit. And then if after COM2 you can also put rectified linear, and that's usually an architecture that people use to do computer vision these days. Is there any conceptual question?
Just going back to the case we were talking about using multiple images.
Yeah.
So what is the scenario that you want to do?
So
some of it is learning from multiple images.
So the input is multiple images because usually an image can be represented by 3 channels, right? Red, green, and blue. So you would rather represent it as multiple images rather than one, because one can only give you a grayscale image.
So will there be cases that you want to use multiple RGB encoded images rather than only one?
Sure. If you have a video, then you might have, per time that you have 3 images, and let's say you take 10 frames, then you have 30 input images, right? And then your filter is instead of looking at one image, it should look at 30 images, right? Is that clear? Did I answer your question?
Thank you very much.
Yeah, cool. I need a question because I feel like conceptually it might be too. Yes.
So how are the filters represented in the COMNet? Like you say that if there are 3 filters, how does it go into the learning products, or which part of the neuron? Does it have to do with the number of neurons that you tie together, or?
So let's say you have 1 neuron in the network. It will look at the moment, I would say, look at this position, right? And they look at 2 images. So let's say this would look like a 2 by 2 pixel. Okay, this thing I draw it out and I put it here, 2 by 2 pixel, and then another image would be 2 by 2 pixel. This is the first image, okay? And this is the second image. Okay, is that clear? Now you have 1 neuron, which is this one right here, right? Right. It's gonna have a weight like that, right? It's gonna have 8 weights. Right? It's gonna have 8 weights. And let's say we index it with W1, W2, W3, till W8. That 8 weights is going to be copied across the images. Is that not clear? Cool. So let's talk about recurrent neural networks.
I had a question on vision. Could you speak a little about tile convolution as well?
Yeah, sure. So right now what I'm saying is that the filters are being shared across the images. Okay? So they are exactly the same at every position in the image. So these 8 weights being copied to every position in the image. But sometimes you don't want that. Right? Sometimes you say, well, maybe only copy if it's very far away. Something like that, right? So this filter will be copied if it's 10 pixels away. Then you insert that constraint in your optimization too. Right? So and then the nearby filters are just locally connected. They're not truly convolution. Right? So that's high convolution. Okay.
And how does it account for rotational invariance?
So supposedly things like a tile, this is basically very good for translational invariance because the filters are exactly the same. So if the object moves left and right for a couple of pixels, because of the type weights and then the max operation, it will be almost translational invariant. But if the weights are not the same, then you could learn rotational invariance as well. Because the weights are not exactly the same, you can pull over different weights.
Okay, but this has to come from the data.
Yeah, it has to learn from the data. I have to move quickly to recover and work. So sometimes you have temporal data, right? And then you want to learn to predict using temporal data. So maybe you want to predict the stock market price tomorrow. So let's suppose that we have active, with the input as active plus 1, the input as active plus 1, etc. Right? Then you want to construct a neural network that can take in information of of temporal. So one way to do this is using the convolutional neural network. And it looks like it's a recurrent neural network. Like that. And then you have so you have a certain white W on the vertical direction, right? And then you have the horizontal connection as well. So you have two sets of weights, the vertical connection and then the horizontal connection. And the horizontal connection are the same, and then vertical connections are the same. And then maybe you want to predict the stock market price. Okay. So this is called the recurrent neural network. Right. And then maybe, so in order to do back propagation, what you can do usual, and then backdrop also as usual, and then sum up gradient for W and V, and W and U, and then update W and V and U using some gradient. Okay. So if you have a recurrent neural network, what you can do is you assume that all the U's are not the same. So you could say U1, U2, U3, UN, and then you have W1, W2, WN, right? And then all you need to do is do forward prop. You look at the difference between your prediction and then copy plus N, and then you do back prop, and then you sum up the gradient for all the UN, all the UI, and all the WI, and then you use it as your update. Okay. I tend to draw that using another figure. Another kind of figure that I tend to draw is something like this. This is the input times T. Okay, so this is another way to draw this figure over here. You take your XT multiplied by W to get some output, and then let's say the representation at time T is time T plus T plus 1, for example, is equal to sigmoid of U and H T plus 0. Okay. So this is H T plus 1. H of T plus 1 is being the sigmoid function of U times H of T plus W times T. So HT is usually recursively defined. And then you could do this.
If you want to predict the stock market for the past few years, for every day or every time step, we end up creating a new mirror and then recursive.
You could say these are the stock prices of all the days in the past, and then it is the last day, and day of, and then you try to predict that. Now, this is basically, it can deal with variable net, because you only have one set of parameters, U and W. So, and it would be on the left. So if you want to predict the next month, you could use it as input. But you could, if you want to predict 5 months later, you could use it directly. That I wanna come back to that in the following. So this is actually successfully used to do something called language modeling. So language modeling is the following. So language modeling is, let's suppose you have you read text, and then you have something called like that, on that, right?
So the goal of language modeling is given the word, this word predict the next word, and then given these two words predict the third word, and then given the three words predict the fourth word, like that. Okay? And then start with a new sentence. Given this word predict that word. Given these two words predict this word. So given words from 1 to 3 predict the 3 word. This is the prediction task. It's called language modeling. So for language modeling, so far we talk about XP being like real value vectors, right? But these are objects. These are discrete variables. They are just symbols, right? So how do we convert these words into XP, right? Some real value vector. So the way that people do it is using one-of-k encoding. So one-of-k encoding works the following. You take your dictionary, English dictionary, and then, sort all the words. And then so this is maybe 20,000 dimensional vector. 20,000. So let's suppose in your dictionary you end up with 20,000 words. Right? Now, in order to convert one of the words to a vector, you can use the following trick. You take a vector and you look at where it is in this vector. Right? Maybe it's at position 15,000. Okay? Maybe the word the occurs at position 15,000 in your dictionary. Then the will be mapped into a vector where it's all zeros. That's from the position of 15,000 it's been at the position of 15,000 it has a factor of 1 and the rest is being 0. So this is called the one-of-k encoding. Okay? And that way you can map every word in here to be a vector. Right? And also the output is also a vector. Right? And then what you all need to do is just put it inside this framework and run back propagation to do the prediction of the next word. Right? And it turns out that using this trick, we can achieve state-of-the-art prediction for the next word. And this is useful for a lot of tasks, for example, machine translation. You also use it for speech recognition because it understands the context, right? And you've heard a lot of things about Chomsky grammar and so on, but it turns out that in real data, a lot of different kinds of grammar doesn't work well, and neural networks usually work better. It's very simple. It's good right here. And the guy who is pioneer for this, his name is Thomas. It turns out that this idea has been, a long time. In 1986, that's a long time ago. But he's done it in around 2000 or something like that.
But back in 1982, in the first paper where people proposed the idea of backpropagation, they already talked about this idea of one-of-k encoding and language modeling using recurrent neural network. Okay? Is recurrent neural network clear? One more thing. So after you multiply this vector, you take xt, which is a 1k encoding. For language modeling, you have 1k encoding. You multiply with w. That action is pretty much equivalent to selecting one column in matrix w. Right? And then you end up with a representation. This representation here is called word vector. Some other people call word embedding. Because you take a high-dimensional vector, you map it into a low-dimensional vector, and then that vector hopefully can capture some semantic meaning of the word. And it turns out it does. And if you look at the word vector, and then you look at their nearest neighbor, right? You look at the word vectors, and then you look at the nearest neighbor. Maybe you visualize a W matrix for different word vectors, then you end up seeing something like this. You know, is equal to you know, Barack Obama, equals to Bill Clinton, you know, Sunday, equals to Saturday, and then maybe Paris, equals to London. Okay, like that, right? You visualize W for each different vector, and then maybe you project it in 2D or something like that. You will tend to see this picture. So it turns out that by doing recurrent training, and you also look at and do one of K encoding, one of K encoding over there, then you end up having very nice representation for the world. Does it make sense?
Yes. For example, the streets were ordered alphabetically, but that doesn't matter. You gave us the example for the K encoding, it's the board like. Yes, the streets are ordered, but the order shouldn't matter.
The order doesn't matter. Okay. Because the order doesn't matter really. It could be any order. It's in an order so that it's easy to predict. Right? But every word, the idea is every word should be mapped into a one-hot vector. Right? All the dimension is 0 except for one dimension. It's not 0. Okay.
Well, can I ask you
Yes.
question about methodology? Hacking question again.
Yeah.
At time t and t plus 1 and so on, you also happen to, if you have a data set, you also happen to have y. So you have y of t and y of t plus 1.
Yeah, yeah.
So you could include those when you're doing the training.
Exactly, right? So that's a very great question. So turns out that if you what people implement this in practice is called unfolding. Right? So what they do is you have xt, xt plus 1, and xn, and maybe in language modeling you try to predict xt plus n plus 2n, right? So at here you also want to predict xt plus 2, maybe, right? And turns out a good implementation is to feed forward and then move forward like this, and then compute backprop at the same time, so that you save the computation. And that's better. It's much faster than that. Yeah. So you take every sentence like this, right? You move feed forward, feed forward, feed forward, feed forward, feed forward, compare with the answer, and then do backprop. Yeah. So that's the actual implementation. Yes.
How does the training dataset size relate to the number of words in a dictionary?
Oh, usually the size of the corpus, it should be like 100 million words or something like that.
It will be usually something like exponential in your dictionary.
I would say that. Your dictionary should be like 100,000 or 20,000. But because it's unlabeled data, right? You can download any text on the web. Right? Because news, so that dataset over here, you could get from news, right? Or any other website. And that you can get as many as you could. Usually we train with 100 million words. The more the better. We also train like a billion words and the results. Okay.
Excuse me. Yes. Is there any way to predict something in the middle, not in the last word? For example, in that example, the set was missing, and you want to use the information after that to predict the word in the middle.
That's a very good question. Yeah, right. So the goal is not trying to predict the back words. So that's not for language modeling. You can do that, but it's not for language modeling. Language modeling is proper. Okay, but it turns out that in order to just learn word patterns, you can do better. Right? So here's an idea. So if you go onto the web, you search for something called word to vec. Right? Word to vec is basically a program that brings in a data set of text and then learn representation for every word. If you download the program, and then it's not a recurrent neural network per se, it's something different. So it turns out, before I move on and talk about network, it turns out that recurrent network is very difficult to train. Because if you have very long neural network, it takes a long time to do backpropagation, right? And then after going through many steps, the gradient vanishes. The gradient vanishes meaning that at the beginning the gradient is very big, but at here the gradient is very small. So it forgets the information from the beginning. So it's very difficult to train. People notice this many years, right? So people have proposed many architectures to avoid the problem with recurrent neural nets. But it's probably not today's presentation. It's still a topic of research. So people want to get by the problem of doing recurrent connections. So another way to get by the connection is not to have recurrent connection, but have something like this. So let's suppose that you have xp plus 1 and xp plus 2. Learn some representation. W, and then you do concatenation. Concatenate or averaging to predict free. And so instead of having connection that way, you do a feed forward that way. So you don't have the recurrent connection anymore, but it's a fixed size window in your text. And this idea is called feed forward. Neural language modeling. And then using this idea, instead of predicting at t plus 3, you could predict the word in the middle. Or using the word in the middle to predict the word in nearby. So you could play around with all these tricks. So work to back use this idea. Okay. But the goal is not to do language modeling, but rather to learn the work factors. Any questions? Okay. I want to talk a little bit about Google Brain. Hopefully I have time for that. Nico? Nico is not here. Alex?
What?
Can you have the...
Oh.
Excited. Okay, so the last part of the talk, we have a lot of pictures, and it's going to be more entertaining. That's not. Okay. Okay, so I'm going to talk about some ongoing projects at the Google Brain project. So first, I want to start out by saying that Google uses a lot of machine learning, right? It uses a lot more machine learning where more than what I can imagine when I was in class. So, you know, when I was in grad school, I thought, oh, Google uses a lot of machine learning. It doesn't use even more than what I can imagine. But machine learning is very, very difficult. Right? Machine learning is difficult is because you really need to require some domain knowledge, domain expertise of the problem. For example, if you do image recognition, you hire people who got their PhDs in computer vision to do design features, right? And then train their model on vision data. But then, if tomorrow you want to do video recognition, then you hire a bunch of other people who got their PhDs in video. And then the day after tomorrow, if you want to do speech recognition, then you hire a bunch of other people who got PhDs. Now, it might work for the current applications, but maybe in the future, for things that we haven't got PhDs for, it might not work. Moving backward in time, a few years ago, when I was a PhD student at Stanford, I thought it would be really great to actually learn representations. So instead of hard coding features, use deep learning, whatever we've seen so far, to learn the features. Right? It sounds today that sounds like, you know, a trivial idea on the hindsight, but it never really caught on in pattern recognition, in mainstream pattern recognition. So it's up to 2011, people still do handcrafted features for a lot of domains. But for us, deep learning works well. It works well for many small problems. It works well when you increase the amount of data, all right? Because it has a lot of parameters. If we increase the size of the model, it works better. And the good part is it requires less domain knowledge. So around 2007 and to 2010, I was at Stanford working on small-scale deep learning, and it works out pretty well. So Google came along and expressed interest in using deep learning in large data scale. And it turns out that the results was very fascinating. So again, the idea of deep learning is to learn representation, layer representation all the way to the top, right? You take X, multiply by some matrix, apply some nonlinearity, get the output, and again, that is the input of the next layer. What's beautiful about this approach is that if you talk about it in computer vision perspective, what it's trying to do is to try to learn representation. For example, at the first layer, you will see something like edge detectors, and then onwards you want to see high-level concepts like face and guts, neuron. So at Google, I work on something called disbelief to represent the fact that I didn't believe that it should work. Right? So I came up with the name that, we came up with the name that, to reflect that we couldn't believe that this thing gonna work. So just try it out. It's distributed belief networks. So the idea is the goal is to create deep learning on many machines, like maybe 100 or 1,000 or even 10,000 or even more, 100,000 machines. And the model is what I told you earlier, the neural network. And there are in neural networks, in general, there are two steps that you have to do. You do forward prop to compute your prediction, and then you do back prop to compute the gradient. That's all you need to do in a neural net. So to parallelize the training of the neural network, what we do is we use two ideas. The first is model partitioning. So you take a neural network, and then you divide it into many machines, right? And the first machine will be responsible for computing the values of these neurons. And then the second machine will be responsible for computing values for these neurons, and etc. Right? And then obviously there will be communication across machines, but we can design the neural network in such a way that communication will be much smaller than computation. Okay. And then per machine, we also have multiple cores to do computation. Okay. And this idea can use up to like 1,000 cores or so. Right? But 1,000 cores is still slow. Right? We want more. We want faster. When we train this model, I realized that it would take months to train a neural network on images, or months to train neural network on speech recognition. And again, this is important because if you train a neural network that takes several months, then if you want to change your mind, right? Maybe the experiment doesn't work out. Maybe the hyperparameter is not good. You want to change your mind at some point. Then if it takes several months, then you have to wait several months to do something again. That's undesirable. You want to scale down that training to be like a couple of days, right? And that's what we succeeded in doing. So the way that we do it is to add more parallelism. So imagine this is one model that we had before. We take our data set and split it into multiple chunks, partitions. So let's suppose that we have 3 million examples. So the first chunk gonna have the first million examples. Second chunk gonna have second million examples. The third million examples, right? And then we're gonna train independent models on each of these data sets using stochastic gradient set, right? And then instead of making the updates at every step, we're gonna send the gradient to something called the parameter server. I think Mu Li has talked about the parameter server, but the idea is simple. You have a few hundred machines sitting in the middle, waiting for the gradient to come in. Right? The gradient mainly P prime, and you wait for P prime to come in, and then delta P to come in, and then make the update and send back. So the conventional way of doing this is to the parameter server gonna sit in the middle, wait for all the answers to come in, take the average of the gradient, make the update, and send back. Okay, that's a conventional way of doing it. Now the flaw of the conventional way is that let's suppose that one of these machines or one of these copies will be slow, right? If one of the machines is slow, and this is real, because let's say if you run your model on 300,000 machines, if the probability of your machine being slow once a year is, is 1 day a year, right? Then if you run it on 300,000, the chance of having one slow machine is actually very high per day. Right? You multiply the probability 300,000 times. So it's undesirable for system that has a lot of slowness and delay and etc. So the way to counter that is to have asynchronous communication. So asynchronous communication, again, the conventional way is to wait for all the answers to come in and then take the average and set back. Now, we don't do that. What we do is at any moment, if any answer comes in, we make the update to the parameter right away. And then, after a few hundred updates, we broadcast the parameter back to everybody. And then everybody replace their own copy with a new copy. And then repeat the waiting again. So it creates a lot of asynchrony inside the network, but it works out just fine. And this way we can actually make up, we can improve the speed, almost linearly with the number of copies. Okay. Is this idea sort of clear? Somewhat? Okay. So at Google Brain, we try a lot of ideas, but it turns out that the simple ideas work out very well. And the two main ideas that we have was model parallelism, which is take a model and then split it into multiple machines, and then data parallelism, and then communicate using the parameter server. That's the two ideas. And right now we can use up to 100,000 cores or even more. I think 500,000 cores is possible now. And because of the speed, so we can scale down the training of something that takes several months to a couple days. And because of speed, we can make a lot of breakthrough in many applications. And I'm going to show you next the applications. So the first application is voice search. So it turns out that one important application for Google and many internet companies is to understand what you say. Right? And you look at the phone and you talk to the phone. You say, "Who is Barack Obama?" And the machine has to transcribe that into some text and then do the search. Right? To do that, it turns out that a conventional speech recognition pipeline has two components in it. Component number one is they take one window in the speech. Let's say the speech is some waveform, right? They take some fixed window like that, and then do some classification to something called a phoneme. So it turns out that human speech has about 800 phonemes, maybe more. A phoneme is a subword. It's not a full word. So for example, if I say Palo Alto, in fact, the phoneme corresponding to that is Palo Alto. Yeah. So there's a lot of that's a lot of effort to it. Yeah. So linguistics actually figure out that there's 800 phonemes. I don't know why. Okay. So the task is to try to have a model to convert the raw input into a phoneme. And then the second model is called a language model that to put all these phonemes together to come up with Palo Alto. Okay? So maybe from the raw speech you say Palo Alto, right? But Palo Alto is more likely. So your prediction will be Palo Alto. And the language model is a recurrent neural net, by the way. Okay? It's going to be trained on text. So the acoustic model used to be a shallow neural network or a shallow architecture. It doesn't work very well. But recently we trained a deep neural network, fully connected, maybe 12 layers, and it works very well. It reduces the error rate significantly from something that doesn't work very well to something that you have today. So if you interact with Android voice search, that's basically the system you have today. And before this belief, it took around, I don't know, half a year to train, but now it should take a week to train with this one. And that's the reason why we can train with a lot more data too. And now you can use it in Android voice search. The second kind of application that we use is in language understanding. And there, we want to learn word vectors. And the word vectors is basically what I presented earlier. We want to learn representation for words so that it can keep the semantic of the word, right? So you want well close to dolphin, Obama close to Clinton, Paris far away, but maybe close to London. Right? And the neural network that we have is very similar to what I presented just before this talk here. It's basically for every word you map through a matrix, and then you concatenate, or maybe you take the average. Maybe you read it through some hidden representation, and then you do classification to predict the last word in the sentence. Simple. And it works out very well. We train it on 1 billion word, and if you type in, and we have an interface where we can look at nearest neighbor for all the word vectors, right? And for example, the nearest neighbor for the word apple with the small a is all kind of fruits. Yeah. That's berries, blueberry, peach, melon, etc. But if you replace with the capital A, Apple, the company, then you end up with Apple's products. Okay? iPhone will be close to iPhone and other Apple products. Okay? So not only the distance between the vectors makes sense, the nearest neighbor makes sense, but the difference between the vectors also makes sense. For example, if you project the word vectors into 2D, and then look at the difference between Spain and Madrid. Madrid is the capital city of Spain. And the difference between Italy and Rome, and then you compare them, it turns out they look very similar. Right? And this is very good for relational extraction, in the sense that let's suppose that I don't know the capital city of Italy, but I know the capital city of Spain. Okay? Then I will take Spain and subtract Madrid and get a vector, and then add that vector into Italy, and then maybe end up here, and then maybe I will nearest neighbor, and then end up with a draw. Okay? And you can use it to learn word vectors for people. You can learn word vectors for Barack Obama. You can learn word vectors for Britney Spears, and then you can ask about all information like profession, age, birth, etc. Right? Using this idea that I show here. Is this clear? Okay.
Yes. I'm feeling polysemy for this. Once you have
multiple meanings?
Yeah. Because a bag is a very different point in that space depending on its meaning.
Yeah. I don't like that question. But I'm forced to answer it anyway, so I will try. Okay, so the question is, what if a word has multiple meanings? Okay, the word bank has multiple meanings, right? For bank, Bank of the River, and Bank of America, right? That's like money thing, right? So if you learn one word vector, then money and river things put together inside a word vector. So it seems undesirable, I guess. First, in practice, it's not a huge deal because it's high-dimensional vector. But anyway, we want to fix that problem. So the way that we fix that problem is in the word vector model, this word vector model right here. During the feed forward, for every word vector, you say every word has 3 meanings. Every word has 3 meanings, and during feed forward, you will have a choice to pick the best meaning to the network. So out of 3, pick the best one. So also a combination of all the words and pick the best one. And then when you do backdrop, only update the word that gives you the best prediction. And that's our goal, just right. Does that make sense? I hope that makes sense.
Yeah,
it seems
makes sense.
kind of clever, but it's not that. But it works out very well. You know, you have bank, one bank close to river and etc. One bank close to money company, etc. Okay, we never published this idea, by the way, but I think if you use it, it doesn't seem satisfying. It doesn't seem satisfying for everyone to have 3 meanings, but in general, if you make it 5 meanings in some way, it's not a problem. But the combination is too high. Anyway, the other application that you could use is machine translation. Right? It turns out that if you learn word vectors for English, and then you learn word vectors for Spanish, and then you look at, you visualize them, and what you see is that they look very similar, the word vectors in one language to the other. For example, here, let's suppose that I know the translation between of 1 to 4 from English to Spanish, right? Then I could learn the linear mapping between this here to this space, right? The linear mapping can be done by just linear regression, one command in MATLAB, right? And then if you let's suppose that I don't know how to translate the word 5 to Spanish, then I could take the linear matrix that I just learned, apply to that vector, and then end up somewhere here. And then if I do nearest neighbor, then I get the word 5, which is the translation of the word 5. Right? So you can use word vectors to do machine translation as well. Okay?
So, in your practice, when you are trying these things out, what are the other words that come in the neighborhood of that point? Say, say for 5, when you try to project the translation of 5 onto Spanish.
Yeah.
And whatever that point was 5 the closest? Were there other closest points? I'm trying to understand what's the precision of this.
Like, the precision is about 90%.
Oh, 90%, okay.
Yeah. Yeah. So we run a lot of experiments. There's a paper on this topic. Yeah. We run a lot of experiments, and we using a dictionary of 6,000 for stuff to learn the linear mapping. Then try to translate the rest of the dictionary. You can get 90% correct. Okay. Sounds good. So we have a paper. Okay. So the third application is in object recognition. So turns out that if you upload an image to Google Plus or Picasa, or maybe if you upload a video to YouTube, then there's a network that look at the video and analyze what the content in the video. Right? And it turns out it's basically a local receptive neural network and a convolutional neural network. But there are 2 papers here, and they run. There are 2 neural networks that look at the image, come up with a prediction, and then publish the prediction. There's a paper in 2011, and New York Times talked about this result, the fact that we can detect cat on the internet. The cat result was a simple autoencoder on the images of YouTube. And then we do object recognition. Maybe I can feed forward a little bit. I think the result is very significant. Like on an ImageNet dataset, the best accuracy that people have, 20,000 categories, right? 20,000 categories. So for any object in every word in dictionary, you have a set of images. The chance if you just give an image and you keep saying cat all the time, you get 0.005%. That's very low. So if you get 10% by working very hard using handcrafted features, right? And then if you use neural networks, you get around 30%, which is much better than handcrafted features, right? And by the way, 30% is 30% on 20,000 categories. So you make a prediction, right? And if it's your prediction of 20,000 categories and it's wrong, even if you predict cat, and if it's like some other type of cat, then you just wrong, right? And for that, we get 30% accuracy. And the network does amazing things. For example, this image right here, when I sent to the network, it's a seat belt. And in order to understand that this is a seat belt, it not only understand, this is the seat belt, but only understand that there's a guy who drives a car as well. For this image, I say that's a chair, but the network say it's a Boston rocker. So it's a specific type of chair. So this it's a accurate. I think that's good. This image right here, I couldn't even tell what that is. But the network somehow figured out that that's a shredder. It's a paper shredder. That's kind of hard because you need to understand that there's some paper right there. And imagine you write a program, right? To actually write a program to recognize this is a shredder is kind of complicated, right? But learning does better than that. So I think that's a remarkable result. So we thought that it's kind of lucky because somehow it does so well. Can we fool it by sending it like cartoon pictures, right? Because during training, we restrict the network not to see cartoon pictures. But at that time, we need cartoon pictures and see what it does. And it works out very well. So for example, this image, if you say that's a face, that image that say, I'm using park, that image and say that's a hammock. I think that's a hammock. One would say that's a cat too. So for the things that it doesn't do very well are objects that are very similar to each other, right? For example, it will be confused between Indian elephant and African elephant. I have no idea. Actually, I ended up reading Wikipedia to distinguish between the two. And then I couldn't say, cassette, malaria mosquito and yellow fever mosquito. I don't know. It also does badly for objects that are very small in the image. Right? For example, this image right here in ImageNet is labeled as plunger. The network say that people, okay, reasonable. Things like this image right here is labeled as snorkel. The network say it's swimming, maybe it's a person, and then swim trunk, and then snorkel. Too late. It's a snorkel. So this image right here, the network says people, then tree. We look at the top prediction, right? The first is people, the second is tree, third is street, and then matching order, and all the way to the end is like ASCII. Too late. Not good. So this image right here is labeled as ping pong ball. That's a ping pong ball. Okay. So there's a lot of idiosyncrasies in the data set, but in general, the prediction of the network looks fine. Okay. When we use it for Google Plus photo search, right? A friend of mine has a lot of dogs. And she uploaded a lot of dogs photos in Google Plus, and then she searched for dog without labeling the pictures of the dog. And the amazing thing is the networks return her pictures of the dogs, right? This, that's a small picture of the dog, right? That's a closer picture of the dog. close up. It's all kind of pictures. Oh, it's amazing. And she's so excited, and she sent me this picture. So I sent up. I give it to you so that as a proof that it works. Okay. So I don't have time, but I would say at Google we work on scaling the training of deep neural networks. We use two ideas: model partitioning and data partitioning, right? And this is the picture that you might remember. And then we applied it to voice search, photo search, and text understanding, and we made a lot of significant improvements on these applications. And Google Brain is a big team. We have around 20 people, 20 or 25 people working on different ideas and new methods and so on. Okay, so I can stop here and might be taking questions. Any questions? I'm so happy that it's clear.
So why did Google spend so many resources in building 100,000 cores? Why not go to GPU?
Good question. It turns out that parallelism across machines and GPUs are like orthogonal ideas. Right? You could apply the idea that I told you instead of on machines with CPUs, machine with GPUs too. So, yeah. We are actually doing it. So. Question.
So that's 30% accuracy is basically for all the categories of the app.
For all categories.
Okay.
For ImageNet, the size of each category is counted. So the number of people in the dataset is the number of people images in the dataset is also equal to the number of baobab trees in Africa. So it's okay. No more questions. Okay, great.
I don't know much about neural networks.
after you've done it's okay. I mean, it seems like the most.
We have okay, the one is so at the top of the guide, they're good. They
What do you want to do?
Yeah, because, well, unless you have like a bunch of developers we can tell them both in the market. You'd be better off.
Well, maybe my house, that's probably what you want. Right? You want 12, you want to have 12 pages by 1024. Oh, yeah.
So
Otherwise, that would look really crappy. Okay,
papers or anything. How many more copies? So just I guess the data sets of classification. We're still not feel with the camera. Sorry.
So okay, let's start. And I know not you guys have some laptops on hand because I know there's a match on the house. So if you CPU power is enough and you can watch video and you can do something else, then go to the GitHub premises and download the code and compile something. So it's quite easy. So you first make a directory and clone 3 repository. One the source and one the library and one the data.
Excuse me, Moon. Could you please turn on the microphone?
Oh, sorry. Could you? Hi. Can you hear me?
Oh yeah, it's working now. Thanks.
Awesome. Okay. So this is the source. This is something you will compile, you will need. So if you compile this one, you get MPI, you get Agnes, you get all the things. So, and this is the data. So if you get this one, you can install iOS script. This takes a while. Maybe you can start now. And after that, I will show you how to run something, how to do these things. So let's start what we talked about yesterday. So we talked about we want to distribute the implementation of the gradient descent. The architecture will do nothing. The machines do not share everything. So if you want to communicate
communicate something, you need to go to the network. And the data center can be right in that. So I think Ed has discussed this morning. And there's something you need to, some delays and some penalty if you distribute things around several machines. Okay, let's start that. So here, if you have the training data, it's a matrix, and you have a model W. Now we first assume the W is not so large, so you can store on the single machine. The problem is that you have a lot of data. So what you can do is that, just like what we have discussed yesterday, you want to run a multi-thread matrix kinds of vector. For the distributed version, it's quite similar. So if we assume this is a row matrix, so you store the instance row by row, what you can do is that you can partition the data onto a row segment. Each row segment goes to one machine. So if you do that, you can run a distributed version of matrix kinds of vector. Give an example here. First of all, the data is stored somewhere, some base, for example, the distributed file system. And you have some model. For example, if the model is not so large, you can just store on a single machine. Next, the first step is that you partition the data onto a lot of machines. Each machine gets one row segment. This is machine 1, 2, and n. Next, this machine get the model from that server. So you get the local model from the server. Now you can start computing. For each iteration, you first compute a gradient. You're using each machine using the local training data, using the local model, compute a local gradient. Next, you want to summation over all this gradient. You get a global one because the gradient is summation over all training data. So you can do aggregation here to get the global global gradient over all training data. If you get that, now you can update your model by just using the current model minus the learning rate times the gradient. This is what gradient is at. Next, so you need to broadcast the new model. So this model, this is a machine, this is a machine, and this is a server machine. So this is the network communication. You need to send the gradient to get the server. The server needs to broadcast the model. So the network occurs on between different machines. Now this is the concept. Now we discuss two implementation. One is that you use MapReduce. So MapReduce is proposed by Google about 10 years ago, and I think it's the most widely used distributed programming framework. On this framework, you need to specify two methods. One is the map, one is the reduce. For the map, you get some data and produce some data. In this case, you present the data by a key value pair. And one key value pair, and then you produce maybe several different key value pairs. For the reduce, for the same key, I reduce all this value associated with the same key. So one single key, several values, maybe I produce a new value and associate with the same key. And then you can produce several types of it. So this is MapReduce. Using MapReduce to implement the gradient descent is quite simple. So each iteration can be viewed as a map and a reduce. On the map stage, each worker compute the gradient descent using the local model, local data, and output the gradient. The gradient can be presented by feature ID as the key, gradient value as the value. So now in the map stage, some machines summation over all these gradient values on this key. So you get the gradient, the global gradient. So how's it good? So this is the programming, and this is what MapReduce have been implemented. So you have each box is a machine. You have some map machine, you have some reduce machine. So that machine can be run at parallel. So this is the map machine. Each map machine reads a bunch of training data, for example, from HDFS. Then you compute the local gradient using the local training data, local model, and you write the local gradient onto its own disk. So if you finish, you tell the master, okay, I'm done. The master then tell the reduced machine, okay, that machine has been done, that job has been done, and now you can read the data from that machine. So this reduced machine get if this reduced machine is managing the particular key, so this guy will read all the key have been produced at the mapping machine by just a read from this local disk. After it's done, after you write, you get the data and then you output the result to the disk something else. So on this case, it's the updated model. So you iterate again. For each iteration, you run a MapReduce, and if you have 100 iteration, you run 100 MapReduce. Now here is the demo shows how do you run a map job. So in this case, you have about 300 workers. That is the machines you have, and you want to run about 30,000 of map jobs, and you have 500 of reduced jobs. The second row means how many jobs have been done. The third row means how many are active are running now, how many jobs are running now. The input data means how many data you want to get from the HDFS or distributed file system. This is how many data you've done and how many data you have been output. In this case, this is the 18 seconds. So now you get about 300 workers, and each one run the map job. So after some while, you get more workers, you get more. Now you get over near 2,000 workers with machines, and now you have each machine runs a map job, and you keep going, and it's done. So all the map has been done, and you have reduced all the output to the local disk. So now you can start a reduce job. Now you start. Okay, then you start. So all the reduced job have is not done. There's still 2. Okay, still 1 and done. Okay. So this is how you run a map and the reduce job. On practice, you want to have more number of maps than the actual machine you have. That is what we use for the thread pool. So if you have 8 threads, maybe you want to have 80 tasks. This is because if you put the task small, that guy can be do load balancing for you. And on practice, do not use MapReduce if you really have a lot of iterations. For example, if we do some feature extraction, maybe you just pass the data a few times, from the raw data, get the feature data to the machine learning algorithm. That is fine. But if you run some optimization algorithms, maybe you want to pass data 100 times. That's a huge overhead. For example, let's look back again. So at the beginning, you only get 300 workers, and you keep going. You keep getting more workers. So this is overhead. You should talk to some cluster resource manager. Okay, give me more machines. Maybe take some whiles. Maybe a lot of people use that. You cannot get the machines. The second is that you need to write all things onto the local disk. So you write all the gradient to the disk. This is also overhead here. And the last one is that you maybe have some stragglers. That means this is the slowest. The 19 jobs are not finished. All the other guys have been finished. Now you have 2. This is the 2 slowest machine, and you have 1. So maybe there's some very slow machines. Put your one MapReduce very long. Okay, but generally speaking, it's the most powerful, simple model you can think about. So the left is another most widely used, especially for machine learning, is the MPI. It's a message passing interface. It's proposed by different group of people. It's by HPC people. And there's 2 widely used implementation. One's OpenMPI, one's MPIG. So I really don't know what is the difference. I know the thing that there's some slight semantic difference between the API for these guys. For example, for the all gathering things, this guy do not assume you have order between all the solutions, but this guy guarantees order. So this is slightly different. But generally speaking, almost the same. So MPI models assume different things. For for example, the machines are viewed as a group. So this is all the machine you have is from group, and all this machine on this group have been ranked by your ID from 0 to n-1. So if you have n processes. This is a problem if some machines die. If machine die, MPI job exists because HPC people do not think the machine can die. The machine are reliable. So, and you have communicators. Communicator means you can communication data between the communicator. The default one is MPI common way. In most cases, you just use it. And you can define your local communication group so that group people can be computed with each other. If we know the data center, what the network connections, you can define something fancy communicators. MPI program is quite simple. So you first initialize something and call some MPI functions and finalize that function. So in this case, it's the simple hello world exam. So you initialize it and you get what the rank ID of this process is. Then get how many processes are there. Then print something. So if you have 4 processes, you will print 4 lines of output. So the difference is that each will get an ID from 0 to n-1.
Question.
Okay.
So the group of processes have to be on the same machine for that to correct?
No, it can be. Yes, you can on the same machine. You can on different machines. Okay, so it's a distributed version. The goal is to have around different machines. I will show you later how to run different machines. So the MPI provides more than 100 functions. If we just want to implement the graded descent, it's quite simple. So you only want to use 2 is enough. One that MPI reduce means each worker provides a local gradient to that function. And there's a global gradient, which will be on the rank 0. So you can gathering all the local things to a particular machine. Here is set to rank 0. Now you tell me how many features, how many entries are here. This is the feature size you have, because the gradient size is the number of features you have. Next, you tell me, oh, okay, what is a tab, and how do you aggregate these things? You do summation over here, and you communicate over all the active process you have. So after this function, the rank 0 machine will aggregate the global gradient over all these machines. Okay, after you get that, you can update your model. If the model is updated, now you need to tell all these machines, okay, now I have the model. It tells you what is the new model. You can call it by broadcast. This is the data on the rank 0. And it tells me how many data you have, what is the tab, and you broadcast to all this process on this communicator. That is all the machines have. So it's almost done. To analyze the performance, this is a figure shows how tactically you run an MPI job. So here's 3 machines. Each machine starts, this is 2 iterations. Each machine starts with computing local gradient. After computing, you do or reduce. You do reduce. That is, you send the gradient to the rank 0 machine. So if the rank 0 machine get all this gradient, now you can update the weight. After the weight is done, you broadcast. That is, you send the gradient, you send the weight to all these machines. And now, if the machine get the updated model, you can now start computing the next iteration. This is not so efficient because you have 2 resources. One's a CPU, computational power, one's a network. So you can run that things at the same time because doing CPU do not use network bandwidth. During sending something, it takes a little CPU power. So in this case, you're using the CPU and the network bandwidth sequentially. You're using CPU now, network 0. Now you use the network, the CPU is doing nothing. And even worse is that there's a barrier, means you should wait all this machine goes to here. That is, you need to wait the slowest machine also goes to here. So if there's some other machine has been done, that machine is doing nothing. So in this case, all this segment has been wasted in terms of CPU power. So the efficient implementation should parallel the CPU and the network vendors. On practice, if your model size is not so large, quite small, and you do some dense communication, that means each time you send a dense vector rather than a sparse vector. So you send the whole vector, and you assume you have reliable machines, the machine you never die. That is the case for your school cluster or your own clusters. And only you are using these machines. That is, you take whole machines, the other guys are waiting for something else. So on this case, MPI is the most efficient thing, I think, most easy thing and the most efficient system you want to have to try. But the things goes too difficult if you have a very huge model. So if you want to do model partitioning, that is what Coq said on the Google brand, and you have some sparse communication. That is, the gradient is a sparse vector because it's a sparse training data, and the model is quite sparse.
Okay, in terms of parallelizing the communication and the CPU?
Yeah, maybe not today, maybe I can show you tomorrow how to do, because now you have relaxed consistency. It's a sequential model, so you guarantee the model is consistency. But if you want parallelism, it means a little bit synchronized distribution. So you need to consider about how the program when the data is not consistent. So you need to consider something about else.
It's possible to update every send the gradient in the journal for every input example at a time.
So yes, you can. What you can do is that you compute a gradient, send a gradient, but do not wait. The model is coming back. You can continue to the next iteration. What will use the old weight? What will use the new weight? I don't know. And so there's some data inconsistency here. Okay, so I will cover tomorrow. And you have more choices. There's a bunch of distributed systems. For example, if you want to compute on the graph back may be the best choice you can have. So, for example, you want to compute the phase run, you want counting on the graph. So, because graph back using a different programming language, so everything's a vertices. And if you really want to run MapReduce, Spark may be the best choice. Spark is like MapReduce, but do not write the data on the disk. Remember that each map needs to write the output to the local disk so that the reduced job can read the things. Spark says that, okay, I can store the data on the memory so that the reduced job can just read my memory. That's it, fine. So this is Spark, and Ref will be presented on next week. And there's a bunch of the other guys. So because I didn't use them before, so I do not give too many comments here. So because it's a tutorial, so Alex tells me, but it's a tutorial, so you cannot cover things too much because Alex has been told what I want to present today. So I'm going to show you some demo, how to run a distributed gradient. Okay. So if
so you run you have MPI run, so your parameter server actually runs on MPI in the background.
Oh no, I just use MPI to start the job. So I do not use MPI's functions. You can use different things to start a job. You can SH to some machines and start the job. So but MPI run, because a lot of clusters have MPI run, so you can easily run a bunch of processes on different machines. And if we do not care about the fault tolerance, so because MPI is quite good, you can control C and everything stop. So if you run some fault tolerance job, you kill something, the other guy still running. So you need to kill a lot of things. Okay, so if you have laptop, you can just run it So it's quite simple. So I can show you some demo how to get things done. So first you need to get the source, and the most difficult one is to install the library. So you can either have MPI here, you have some Google library here, and you have some communication library here. And also you have icons we presented yesterday. And there's some small data. If we want to go large data, that's, yeah. Okay, so if we want to, there's a Google Drive link, so you can get the small and large data, about 1 gigabyte of data. So because Dropbox is out of space, so I put on the Google Drive. Okay, so the first step is that you first clone this. Okay, if you get the code, you need two things. One is the library. So it takes maybe several minutes to compile. So I have already compiled, so you can just link something here. The next thing you need to get the data. So I already downloaded. So. Okay, so you can compile the things. You can make, and you can use multi-thread maker. So you can specify how many threads you want to have. I use a thread now. So you can compile the things. Hope everything goes fine. Okay. So go to binary directory. You get, in fact, two things. You can make all the test binaries by using Mac test. So this is the primary server binary. This is MPI because this one can be started by an MPI one. Here you can just use it using a primary server, so you can start by every convenient startup you have. And this is you convert the text training data on the binary form because it's much easier to read a binary format rather than text. Otherwise, you need to pass the strings onto some integer or float number. It takes a lot of time. So what you can do is that you first use MPI run. MPI run is shipped with MPI. So you can run, for example, you can create 8 thread, 8 process, and then you run some command. You can, for example, just like that. So now you can create 8 process of the primary server instance. And now you have some server choices. You tell me how many number of servers you want. This case is quite simple. You just one service is enough. Next, you tell me how many workers you want. That is how partition the data into different work groups. So each one will get partition of the trained data. And for each worker, you tell me how many threads you want. That is, for sparse matrix, how many threads I want to compute matrix times a vector. So next, you tell me what is application you want. I can do some pretty simple. I will show you how that configuration happens. So now you can get something. Now this is the training data you have. It's a very small data set. It's RCV1 data set. You have about 20,000 of examples and about comparable number of features. Now you know the data, and you can ignore this now because maybe we can talk about if you want to run block coordinates and block something, you can. And it's very efficient during the synchronized communication. The next thing is that for each line is one iteration, and show the number of object functions you have, the relative object changes. So and they show you how many non-zero entries on the model. So if you want run sparse logic expression, you get small number. The last 3 columns is you can ignore the first 2. The 3 one is that the total number of second you use on this iteration, because this is quite slow, but this is quite small, so this one, this is next 0.1 second. And the last thing that you have create one server and two workers, and just show you how many data you have been sent, how many data you have been received. Okay, so now let's go to the configuration. Okay, the configuration is here. So it first tells me this is a risk minimization task. You have made different dependent tasks or something like that, and it tells me what is the name of this application, what is the parameter name. So because you can run several jobs at the same time, you need to tell a unique name here. And next, it tells me what data you want. This is the data on the buffer format, and this is a regular expression shows, okay, this is the data you have. Next, because it's the risk minimization, the loss plus a penalty. The loss we use is a logistic loss. The penalty we use is L1, L2 equalizer. Because the coefficient is 0, actually this is nothing here. Next is the optimization you want to use. Here's we use gradient descent here. For the gradient descent, you want to specify the learning rate. We use a very simple strategy here. You fix the learning rate to 0.01. The last thing is that it tells me how the iterator goes. You max pass data 40 pass of the data, and if the relative object function is less than the epsilon, you stop. So this is the ordinary parameter, ordinary things you want to specify to a learning algorithm. What you can do is that you can change the learning rate and see something. For example, you can enlarge the learning rate and run something again. Okay, so after 40 pass of the data, you go line E to about. So if you choose a small learning rate, okay, you get a large object function. That means now you can safely, using a large learning rate and get more converge rate. And you can try even larger one. Okay, this time something's wrong because using a large learning rate, you find the converge rate is less good than the small learning rate here. Okay, this is a very small data set. I can use a slightly larger one. So I first test what data I have. Okay, this is this is a slightly larger one. The CTRA we have shown yesterday, it have about 4 million of examples, about 70 million of features. So let's look at the, so each is a part. We have already partitioned the training data onto several parts. Each part has the binary we call IO format. Each instance is a product buffer binary forms. And you have the information here. Let's look at one information here. So it shows that you have several individual feature groups. So you have the group ID and how the feature of this group start, how the feature group end. So we will show tomorrow how to take advantage of the feature group, so to accelerate the optimization rate. In this case, for the gradient descent, we just ignore this information. So, and this is all group information is you have on this partition you have about 100,000 of instances and about 1 million, 10 million of non-zero entries on this data, and you have about 32 part of the data. Okay, so how to run this data? You just change the file here. And okay, you can stop. this time you have about 4 minutes of examples and about 40, 60. So never mind. So you know the data cost 6 seconds, and now something goes wrong. So you get the infinity grid object function. So usually that means you have too large learning rate. That means you work too along this direction. Remember that if the data is quite sparse and you set a very large learning rate, you maybe something goes wrong. There's two things you can try. One that using online search to guarantee each time you have a proper learning rate. The other is more simple. You just decrease the number of learning rate. Okay, let's do it. Okay. So here we use a small learning rate. Let's try it again. Okay, still something else. So let's try it. Even smaller. Let's even smaller. Okay, this time it's working. So that means if data is quite sparse, you need to have a very, very small learning rate. And this is the last is each iteration using 2 seconds. Now we use 2 workers, 2 threads. In fact, you have 4 threads. Remember that each iteration you're using you use a matrix times a vector and the matrix transposition times a vector. On yesterday, we showed that each operation costs about 4 or 5 seconds. So in total, you have 1 second. Now you have 4 threads, this goes to 2 seconds. So generally speaking, the system overhead is not so large. But now you look at that, so this converge has some problem. So what we can do is that, remember that if it's sparse data, the simplest one you can have is that you're using an adaptive gradient. So now I show you how to implement the adaptive gradient on maybe 3 lines, 4 lines of code. Okay, so let's go to the, let's think about it. Okay, here's the gradient descent, the implementation. So you have two operations. One is computer gradient, one is update the weight. So on computer gradient, you using the loss, and the computer first gradient, given the data, training data you have, given the output is a gradient, one gradient. So, okay, let's look at the loss. The loss function is on loss, longitude loss. So this is the loss, implement the loss function. So you have 2 functions. One is evaluate the loss. On longitude loss is log 1 plus exponential minus y times. This is a vector, and store the vector here is x times w. It's a vector as long as the number of examples you have, and you summation over it. So this is the object. This is the object function of this loss. And the second is means you compute the first order, all the diagonal second order gradient. So if you plot these things, the first order is that given these 2 guys, you compute tau and transport x times minus the label times this value. So this is how you implement the same method. So the primary server presents all these things as a local sparse vector, sparse matrix. So you can use it eigen3 to write something like MATLAB, and you do not need to consider about how to do communication, how to map in, I will show you tomorrow, how to map in global feature ID onto some local, convert to a local slightly dense data structure. So now if we want to implement the adaptive gradient descent is that on this case, you get a weight. You get eigen format of the vector minus the linear rate times the gradient. So this is an ordinary gradient descent. If we want to have adaptive one, it's quite simple. It's quite simple that you aggregate all the gradient, all the passive gradient, and each time you update the linear rate divided by the aggregate passive gradient. So what you can do then, you first copy. This is long eigen. This is eigen array with a temporal t, maybe a double or float. And this dynamic means one through one fixed to view one dynamic means it's a vector. And so you define a delta. It should be a summation over all the passive gradient, the square of the gradient. So next, you first say, okay, this is a gradient, this gradient on the array format of eigen. So I can have the vector formation and the array formation. So on the array, all the operations are element-wise. So next, if the delta is empty, zero. So that means this is the first iteration. You just set delta equal to the gradient square. Sorry, what is the square? Yes, so the element-wise square of the gradient. If it's not, you summation of it. Okay, so during update, minus linear rate times the gradient, but you divide by the delta, and okay. So this is adaptive gradient descent. Now you compile it. Sorry. Okay, so you can run the job again. Something goes wrong. That means this is not a number. That usually means you divide by 0. So this means there's some empty feature here. So divide by this guy. This guy may be a 0 here. So what you can do is that simply you just minus a very small number here. Okay. So let's divide again. Okay, awesome. So, okay, something goes wrong.
I can
let me look at. Oh, hey, you mean this one?
I don't know, it would be
This one, this one. Mm-hmm. Let me debug it. So this is what I implemented some minutes ago. This goes well, but never mind. So what you can do is that, what you can do, maybe there's nothing wrong, but the learning rate is too small, so you didn't change everything. Maybe. So next, sorry. Like that. So you can do that just using a large learning rate to see what things happen. Okay. Okay, that's perfect. So if we do not use adaptive gradient descent, you should use a very, very small learning rate. Guarantee that you can still converge. If you use an adaptive one, you can use a very large learning rate. So on this case, you get after maybe 30 passes of data, you get 1.4 E3. Now you get larger. So that means you can use an even larger learning rate. Try a larger one. Okay, this guy looks much better. So it goes to line E5. This is much better than you fixed using normal gradient descent. It goes to 1 something E2. Hello?
Is it possible to select line search, or one has to implement it by himself?
Yes, you can use a line search. I didn't do that because you need to write more code.
Thank you.
So on practice, I think gradient descent is not the most widely used one. It's expensive. If we really want to use gradient descent, you just use it SGD with manufacture. It's even fast. And each iteration uses less CPU powers. And on that case, maybe you do not do linear line search, you just use a decay learning rate. That's fine. And in most of the cases, you maybe use LBFGS and you do some learning rate search. And the use of gradient descent is fine for the fine. So because a line search leads several paths of the data and a lot of synchronizations. So you can do that. You may be just choose the linear rate by hand. So, okay, so I can try the largest one you can have. Okay, so using adaptive one, that is much better. And okay, you can use an even larger one. Okay, slightly better. Sorry, no. This is E6, this is E7. So a larger one do not work. So maybe this one is the best thing you can have. Okay, I think finally I think my time is out. So there's a match you can have on it. So I can leave the thing to tomorrow. Okay. Thanks.
看完样子，那我去一下。好。OK。
还有2分钟的时间。
还行，我觉得这儿刚刚
Yeah, so come with me. I'll show you a good perspective.
Yeah, we'll also need to
the broadcast
Well, go there and stop the broadcast. It will be self-evident.